Hello, Stat 135 students. It's another wonderful summer day doing stats. Wow. Well, today we had an action-packed agenda. We computed the CI for estimators using both parametric and non-parametric bootstrap. We talked about large sample theory for MLE estimators, Fisher information, and the Kramer-Rao inequality. So we're going to start continuing our conversation about confidence intervals using Bootstrap. So this is discussed in 853 in the book. The setup is that we have theta hat as an estimator of theta, and we're going to pretend right now that we know the true value theta naught of theta. We also are going to pretend that we know this distribution. So then we can find the alpha over 2 and 1 minus alpha over 2 quantiles, and find, just as we had before, what the 1 minus alpha 100% CI of theta naught is. So, but in general, we don't know theta hat minus theta naught, what that distribution is. In particular, we don't know what theta naught is. So how do we go about finding these quantiles, A and B? Well, so what we do is we bootstrap. And so what that's going to entail is, so if it's a parametric bootstrap, we're going to make a model of what we think our distribution is, take many samples from that model, and compute the estimator from those models, and subtract that from one, say, your first estimator. So this is going to give you basically a vector of numbers. So you can make that histogram and find the quantiles that you need. If you do a non-parametric bootstrap, you would have your original sample, and you would just resample from that sample many times, each time calculating what the estimator is, and in that way you would also get a distribution, and then you would subtract off again, say, your original estimator, and which is just a fixed number, and then you're going to have a histogram and find the quantiles that you need. So then it's just about how you're going to implement this in R. So we use the quantile function, and I don't think I'm going to say anything particular here, but let's just quickly look at the R code that's on B courses here. So when we do a parametric bootstrap, we're going to start by getting a sample from our population, making a histogram and guessing a model that fits that histogram. Then we're going to estimate the parameter. We're going to estimate the parameters, perhaps using a MOM estimate. And once we're happy with our model, then we're going to draw samples from that model, and that will give us our sampling distribution, and then it's easy to find the SD in that case. So visualizing the sample, here I've sort of cheated. My population is just a Poisson 1, and so I'm drawing from that population. which of course looks like a Poisson 1, but I have a sample, and so when I do a mom calculation, I actually get, in this case, 0.89 for my estimate, for my lambda estimate. So it's not quite 1, but that's the randomness that you have. And this is how it fits the data. It looks reasonable, like a reasonable fit. So I'm going to repeatedly draw from my model, and then I'm just going to calculate the SD of this vector of means, and that is your SE. So you can also calculate the SE using a non-parametric bootstrap, which is what you did in section yesterday, and that's more or less the same. Just note here that that in this step right here, where we're taking our sample from my data. So you're drawing from my data with replacement many times, calculating the mean from each sample. That gives you a vector of means, and then we're just taking the SD. So we get similar results, and you can do a CI calculation, and here so here's the formula for the CI that was computed up over here. So you can compare that. Okay, and